Testing, 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 testing. All right. We are live. Welcome to another HooPost stream. Today we're looking at a paper on the Windows computer here. We do have the NVIDIA eye tracking turned on, so I'm going to be staring at the camera. Just be aware. The paper we're going to be looking at today is called What Do Vision Transformers Learn? A Visual Exploration. This is actually a preprint, so it hasn't been released. This paper actually a little bit older, 13th of December. But yeah, this is kind of an interesting paper that looks at kind of what are the different features that vision transformers are actually learning. Reminiscent of some of the very early Google papers where they looked at what was in the multiple in-between layers of a ConvNet and what the different feature maps look like. And it seems like this is basically that same kind of energy but applied to vision transformers. All right, so let's get to it here. Maybe get this microphone a little bit closer. Vision transformers are quickly becoming the de facto architecture, yet we understand very little about how they work and what they learn. While existing visual studies analyze the mechanisms of convolutional neural networks, analogous exploration of VITs remains challenges. We observe that neurons in VITs trained with language models are activated by semantic concepts rather than visual features. Okay. Interesting little observation there. We explore the underlying differences between VITs and CNNs and find that transformers detect image background features just like their convolutional counterparts, but their predictions depend far less on high-frequency information. Yeah, this is interesting because this is work that someone found where CNNs overfit to texture. Yeah, this is a great paper back. But in this paper here, basically researchers found that ConvNets have a tendency to overfit to textures. So here, for example, this is the texture of an elephant, this is a cat, and then if you basically apply the texture of the elephant to the cat, you pretty much get the elephant. So ConvNets are looking at texture, or another way of saying that is high frequency information. And it seems like what they're saying here is that vision transformers are a little bit better at that, and they will focus on not just the high frequency or the texture. On the other hand, both architectures behave similarly in the way features progress from abstract patterns to concrete objects in later layers. Yeah, this kind of natural creation of hierarchies of abstraction that happens in deep learning, where you have multiple layers of neurons, so that the last layer most likely discards the spatial information and behaves as a learned global pooling operation. We conduct large-scale visualizations on a wide range of VIT variants. So they try out a bunch of different transformers and validate. Okay. Despite their enthusiastic adoption, the constant introduction of architectural innovations, little is known about the inductive biases or features they tend to learn. While feature visualizations and image reconstructions have provided a looking glass, these methods have, this is the actual paper that I was talking about, Ola 2017 paper. That's the one where they showed that ConvNets kind of hallucinated stuff. Understanding, which are difficult to visualize. In this work, we show that if properly applied to the correct representations, feature visualizations can indeed succeed on VITs. This insight allows us to visually explore VITs and the information they glean from images. Okay, so top left image in each category. Image optimized to maximally activate a feature from layer 10. Rest, 7 of the 10 ImageNet images that most activate the feature. Okay, so this is actually the feature inside the Vision Transformer up here from layer 10. So you can see some skulls, some kind of teeth, maybe tombstones, maybe jagged edges. And then the other 7 images here are the ImageNet images that most activate that feature. So it's actually quite interesting how these don't necessarily look super similar from a kind of a texture or even a content standpoint. It's really the concept, right? The concept of morbidity here. It's kind of cool to think about. All right, here in figure 1, we have the progression of a VIT B32. I think we learned that B is actually the small one. This is a small transformer. Features from early layers capture general edges and textures, so these are kind of early layers. And then as you go deeper and deeper into the stacks of these transformers, right, you're going to have multiple transformer blocks. As you get higher and higher, further and further away from the output or the input, your features are going to get a little bit more semantically meaningful. So here you can see kind of little parts, maybe the beginnings of trees, the beginnings of people, mugs, pants. Features evolve, more specialized image components, and finally more concrete objects. So it's an interesting thing is that 10 years ago, more than 10 years ago now, but computer vision, you would actually hand design these. There was these little edge filters and texture filters and pattern filters that would basically, people would hand design these, and then they would convolve their image with these hand design edge and texture filters, and then they would have higher level abstractions on top of that. So now all of these are basically learned by a neural network, but it used to be the case that these were actually designed. In order to investigate the behavior of vision transformers, we first establish a visualization framework. By detecting and visualizing the internal representations, this is in transformer architectures, we find that patch tokens preserve spatial information throughout all layers except the last attention block. Okay. The last layer of a visual transformer learns a token mixing operation akin to average pooling. That's kind of interesting. Such that the classification head exhibits comparable accuracy when ingesting a random token instead of the class token. After probing the role of spatial information, we delve into behavioral differences between the VITs and CNNs. When performing activation maximizing visualizations, we notice that VITs consistently generate higher quality image backgrounds than CNNs. Okay. So maybe CNNs learn to ignore the background. We try masking out image foregrounds and find that VITs consistently outperform when exposed only to image backgrounds. Okay, so transformers are doing a little bit more, are being able to extract a little bit more signal from the background. Convolutional neural networks are known to rely heavily on high-frequency texture information. I think this is this paper here, Garrios. Yep. Find that VITs perform well even when high-frequency content is removed from their inputs. While vision-only models contain simple features corresponding to distinct physical objects and shapes, we find that language supervision in CLIP results in neurons that respond to complex abstract concepts. A music neuron that responds to a wide range of visual scenes, and even a deaf neuron that responds to the abstract concept of morbidity. That's the one that they're showing here. Uninterpretable and adversarial behavior occurs when applying standard methods of feature visualization to relatively low-dimensional components of a transformer-based model, such as keys, queries, or values. Yeah, so transformers have like kind of the core parts of a transformer are these different tensors here. What's called the keys, the queries, or the values. The way that Karpathy just kind of like intuits these, the analogy he uses is that values are basically you could think of where when you break up the image into these little patches, each of those little patches is going to pay attention, right? You're going to have this basically this attention, which is, you could think of it just like a multiplication, a dot product, but you're not doing the dot product with the actual value of that little feature. That little feature is creating a key, which is basically a here's what I am, and then it's or here's what I'm looking for. Then queries are here's what I want, and then that's kind of how the dot products work out. So there's like where was I going with the Karpathy? So the Karpathy analogy here is that keys and queries are almost like a language that are created to communicate between the different feature vectors. So that's one way to try to understand keys, queries, and values, or you can just think of them as kind of this black box tensors that are multiplied against each other. Applying these tools to relatively high-dimensional features of the position-wise feed-forward layer results in successful and informative visualizations. Okay. Oh, interesting. Okay, so they have their contributions, and I've never seen this before, but they use kind of bolded Roman numerals to list the contributions. Patch-wise image activation patterns behave like saliency maps. Okay. Highlighting the regions of the image a given feature attends to. Okay, the model preserves the positional relationship between patches instead of using them as global information stores. Yeah, so when you're doing vision transformers, you're pretty much, I think, I don't know, obviously there's a bunch of different types, but I think pretty much all of them have some form of positional encoding where you're actually explicitly passing a vector that represents where in that image that patch comes from. But in convnets, especially older convnets, there was this problem where basically there's this kind of inherent translational invariance, right? Which is actually a benefit where a dog in the top left corner of an image and a dog in the bottom left corner of an image are both seen as a dog. But sometimes that leads to that invariance, that translational invariance can lead to kind of an issues where the placement of the object in the image is actually not important, and sometimes it is, depending on your application. So transformers have that nice property where because of the positional encoding, the position of the object in the image actually matters. So in situations or in images where the positional relationship between different things in the image is important, transformers are a little bit better at that. We compare the behavior of VITs and CNNs. VITs make better use of background information and rely less on high-frequency textual attributes. Yeah, so this is what we're saying here. I showed this image in the beginning of this stream, but convnets will overfit to the texture. So if you take an image of a cat, apply the skin of an elephant, as far as the convnet is concerned, this is now an elephant. So sometimes people call these high texture or high frequency and low frequency information. So high frequency is things like texture, and then low frequency would be like the shape of this cat. We investigate the effects of natural language supervision. We find that clip-trained models include various features clearly catered to detecting components of images corresponding to caption text. Okay, so not only are they kind of showing you what the intermediate representations of a vision transformer are compared to a CNN, but vision transformers are now also very much used for this type of contrastive training that we've seen before, especially contrastive training with both images and text. This is extremely common now, right? So it's interesting to kind of see. We kind of get a bonus where they show us how this additional supervision from language data sets is impacting the features of image models. Related work, optimization-based visualization. One approach to understanding what models learn is using gradient descent to produce images which convey information about their inner workings. This is called saliency. Is to optimize over input space to find an image which maximizes a particular attribute of a model. Yeah, so you say, okay, this neuron right here, what changes in earlier neurons would produce the maximal activation for this neuron? Okay, you have a couple papers that were doing this. Apparently there's a 2009 paper, which is pretty cool. This is the one that I remember, the 2017 OLA paper. You guys have probably remembered this one as well, 2017 OLA activations. Yeah. Specifically this one, I think, yeah. So these are all convnets, right? And this was basically a similar type of thing where they went through the convnets, and then they would take a specific neuron in the convnet, and then you basically just see which of the neurons before and then before and before, which of the neurons are kind of maximally activating this neuron. And here it's which feature maps are maximally activating that neuron, and so on. And you can go all the way to the kind of lowest layers of the convnet. And largely what this kind of thread of research found is that convnets do kind of have these abstraction layers where at the lower, closer to the image, they have basically patterns and things like this, edges, patterns, textures, and then as you get higher and higher up, the concepts become more and more abstract. So here you're starting to see bugs, dogs, people. So this is the paper we're reading now is largely that same thing, but applied to vision transformers. Okay, so there was people that did this in 2021 for vision transformers. Aside from optimization-based methods, many other ways to visualize CNNs have been proposed. Okay, you have a couple different people. Saliency maps, these are great. If you've never used these. Identifying what parts of an image are important to the model's classification output. So like, yeah, this is what a saliency map looks like. It's basically, you have an image. Wow, that's terrible. Look at all this crap that they're trying to spam on us. But this is better. So here you can see with this image, and you can basically it's not looking at the intermediate layers, but it's literally projecting that, doing that same kind of approach, but all the way to the image, and then it'll show you on the image itself which parts of the image are maximally responsible for causing that final prediction, right? And it gives you a really good idea about which parts of the image is a convnet or any neural network paying attention to. There's a bunch of different packages, Python modules and so on that can do saliency. maps for you. Okay, so VITs are inherently robust to many kinds of adversarial perturbations and corruptions. Like many visualizations, we take gradient steps to maximize feature activation starting from random noise. Okay. To improve the quality of our images, we penalize total variation and also employ the jitter augmentation and color shift and augmentation ensembling. I guess this just means applying multiple augmentations in a sequence. Finally, we found that Gaussian smoothing facilitates better visualizations. Each of the above techniques can be formalized as follows. Okay, so this is the actual formal way to create feature map visualizations from a vision transformer. You start with a patch P of an input X. So vision transformers break up an image into patches. So let me see if I can get a good image of that. Vision transformer patches. Yeah, this is a good image. So why does that image suck? Let's do this. Open image in new tab. Wow, that image is resolution quality potato. How about this one? Open image in new tab. Also potato, but you basically get the idea, right? You take an image, and then this would be a VIT9, right, which breaks up the image into 3x3 grid of patches, and then each of these is a patch. So here, patch P would be one of these little patches, and input X would be the actual full image. At layer L, so you're gonna have a bunch of these different transformer layers all stacked on each other. An array A, L of P with D entries. We don't really know what that is yet. We define a feature vector F to be a stack composed of one entry from each of these arrays. Okay. Let FLI be formed by concatenating the ith entry into ALP for all patches P. This vector F will have a dimension equal to the number of patches. The optimization objective starts by maximizing the sum of the entries of F over inputs F, X. Okay. So this seems like a little bit needlessly over-defined to the point of confusion, but let's actually break it down. It's probably simpler than we think it is. So you have the input image X, you have a specific layer that you're interested in, and then you have I, which is, I guess, basically just a way of creating different ones. So here you would have, let's go here, right, I would be maybe this dimension here, so here you have 4 different activation patterns, right? So it kind of seems like maybe that's what they're getting for there, is like the I is just to have a bunch of different candidates. You're summing over all P, so all patches in the image, and you're summing this FLI. I don't know why there's a parentheses P here. I don't know what the fuck that means. But basically for all P, for all patches in the image, you're summing up these feature vectors. And that's the loss. So the magnitude of the feature vectors is basically what they're trying to minimize. Maximizing the sum of the entries of F. Okay, no, you're not okay, so here's the thing. You're not, what you're ultimately doing is you're trying to produce an input X at a specific, that for a specific layer L, maximally activates, right? So basically the F is like the features. You want the magnitude of those features to be as big as possible. So this is basically just a long-winded way of saying we want maximal activation of this feature vector F, right? Maximizing the sum of F over all patches in the image. We employ total variation regularization by adding the term lambda TV x to the objective. Okay, TV represents the total variation, so total variation, TV. And lambda is the hyperparameter controlling the strength of its regularization effect. Okay, so there's an additional term to the loss here, right? So you have this regularization term, you have your main loss here, and then you have a regularization term, and you're trying to find the x that maximizes that. We can ensemble augmentations of the input to further improve results. Let script A here define a distribution of augmentation, so this is just augmentation function. And let A be a sample from A. Okay, so you have a set of augmentations composed of many smaller individual augmentations. We sample several augmentations, so K total augmentations. So you have a set of total of all possible augmentations, and then for each problem, you're going to subsample a smaller set of augmentations, specifically K amount of augmentations, and each of those is going to be lower letter A. So you can see here how the input image X, the augmentation is being applied to the input image X. And you're not you're not applying these augmentations one after the other. You're actually not summing them until here. So you're calculating the loss for each augmentation separately, and then summing together all of the losses for all the augmentations. That's important here. We achieve the best visualizations when A is GS-CS jitter, where GS denotes Gaussian smoothing, CS denotes color shift. Okay, so these are just different types of augmentation. There's a nice image augmentation library that I would recommend. It's called ImageAug, but for example, Gaussian smoothing is something like this, right? Gaussian noise. Where's Gaussian smoothing? Additive Gaussian noise, dropout, coarse dropout. We want smoothing. There you go. See also filter smooth. Yeah, this is what a smoothing filter kind of applies, right? It kind of makes it more and more fuzzy. Let's see, what else do they have here? They said color shift. So what does color shift look like? Color shift. So these are different types of color shifts here. You have color temperature, hue, multiplication, different contrasts. And then jitter. Jitter usually refers to kind of the position of the object, so something like this, right, where you're actually just like zooming in or rotating or jittering. Let's see if they have an exact. There's nothing here that uses the word jitter, but you can kind of figure that out, right? That's usually the most common one. Okay. Here we go. Gaussian basically just takes your image and applies some noise, where the noise is sampled from a normal distribution with 0 mean and a variance of 1. Color shift here takes your image X, multiplies it by this little sigma here, which is a unit. This is a uniform distribution from -1 to 1. The exponent of that, and they're adding this little mu here, which is also from a uniform distribution. So it's basically just taking your color distribution, right? Think of you have some Gaussian that represents your color, and then you're just kind of shifting it. Note that even though sigma and mu are both additive noise, epsilon, getting my Greek letters confused, they act on the input differently since mu is applied per channel and epsilon is applied per pixel. To better understand the content of a visualized feature, we pair every visualization with images from the ImageNet validation train set that most strongly activate the relevant feature. We plot the feature's activation pattern by passing the most activating images through the network and showing the resulting pattern of featured activations. Figure 3a. Figure 4. Okay, so we saw figure 3a. Example feature visualization from a VIT feed-forward layer. Image optimized to maximally activate a feature from layer 5. Center corresponding maximally activating ImageNet example, and then right the image's patch-wise activation map. So this is the image here. So this is the image that maximally activates this feature here, and then this is the patch-wise activation. So this is a VIT 32, right? They set up here VIT 32, which means there's 32 patches. So this right here is actually probably 32 by 32, and this is like the, actually no, that doesn't look 32 by 32, but basically it's showing you which parts are attending to which parts. So you can see here, like roughly it's tracing out the lizard, right? Or which patches, patch-wise activation map. So which patches are activating the most, or the activations, I don't know. Either way, this seems to be tracing out the lizard, and then here it seems to be paying attention to specifically this the legs of this shopping cart. And you can see here how this shopping cart is what maximally activates this little feature map looking thing here. And here with the lizard, it's really just the pebbles. So it's like the texture of these pebbles is kind of what's causing it. Okay, where were we at? Okay. Interestingly, the gravel background lights up in the activation pattern, whereas the lizard does not. Ah, okay, that makes more sense. So in this case, white means high activation, black means no activation. All right, that's a little bit, that makes a little bit more sense. So now it makes sense that this here, this gravel pattern, this pebble, this kind of like bubbly rock pattern is activating very much on this, which is the background, right? And then here, these kind of like lines, right? This like kind of mesh line pattern is activating very much on this part here of the shopping cart, even the wall in the background, right? Because the wall kind of has these lines as well, but it doesn't activate at all on this kind of like fire hydrant sprinkler stuff that's sticking out there. The model we adopt for the majority of our demonstrations is a VIT B16, so 16 patches total. Conduct large-scale visualizations on a wide range of VIT variants. 38 models in total, 38 different vision transformers. VIT B16 is composed of 12 blocks, so that's 12, not 12 patches, but 12 attention blocks, one after the other. Right, each block is a multi-head attention layer, followed by a projection layer for mixing the attention heads. So basically, it's a multi-head attention, followed by a fully connected neural network layer, just kind of a standard little layer. Sorry, I need to blow my nose here. In this model, every patch is always represented by a vector size of 768 except in the feed-forward layer, which it has a size of 3072. We first attempt to visualize features of the multi-headed attention layer, including visualizations of the keys, queries, and values. We find that the visualized feed-forward features are significantly more interpretable than other layers. VITs pack a tremendous amount of information into only 768 features, which then behave similarly to multimodal neurons. Okay, so it seems like one of the things they're saying here is that just the way that transformers work, there's a lot of information that's going on in those vectors, the keys, queries, and the values, right? It's like you're ultimately, you want the dot products of those, of the keys and the queries and the values to be really high when they're related and low when they're not related, and like they end up being related in the sense that they're close together in this like high dimensional space that's like very difficult to understand as a human. So that's kind of what they're saying here, is that these key, query, and value vectors are difficult to like visualize. It's not like a ConvNet feature map which you can look at and kind of have an idea of what's going on. This behavior is more extreme in deeper layers. Okay, so here you have the actual key, query, and value visualizations. High frequency pattern and adversarial behavior dominate. Feed forward layer. Okay, so yeah, this is like, I have no idea what I'm looking at here, right? It looks like, well, one thing you can kind of glean from this is that it is high frequency, right? It's like you kind of, the frequency of this, there's like this red, green, red, green, red, green, red, green. So there's like this alternating up and down, right? So there's some, you could like loosely fit a kind of like a sine and a cosine, a wave, right? A repeating pattern to that, and that repeating pattern has some frequency, and that's kind of why people refer to this as high frequency, because there's just a lot of lines over the whole image. If it went kind of just like white, then black, then white, then black, then you would call that low frequency, right? So here you have some low frequency stuff, right? Because there's a pattern here that happens in the order of just like kind of a couple things wide per the image, and then you have this high frequency pattern where you have maybe 100 things wide per image. It's kind of a terrible description, but I'm trying to like kind of build intuition here for what a high frequency versus low frequency pattern is. So these are the key, query, and value vectors, but up here on the right, this is the feed forward layer. So you can see here how there's a little bit more meaning here. You can actually maybe pick individual things out with your human eyes. Like here, there's some kind of patch. There's something going on over here, right? With this like circle feature and then this larger kind of blob. But this is still very hard to try to understand what's going on by looking at that. Feed-forward layer depicted in Figure 5 takes an input of size D768, projects it into a T equals 4 times higher dimensional space. Yeah, so I mean, this is why it's hard to visualize as a human, right? Like, you're visualizing a 768 dimensional space being projected into a even higher dimensional space, right? Like, humans are only intended to really understand 3-dimensional space and maybe 4-dimensional space. So, like, 768 dimensional space is just not going to be, it's not going to compute in our brains. Unless otherwise stated, we always visualize the output of the GELU, right? This is like a ReLU, but a Gaussian version of that. Hypothesize that these networks exploit these high dimensional spaces to store relatively disentangled representations. On the other hand, compressing the features into lower dimensional space may result in the jumbling of features, yielding uninterpretable visualizations. The VIT feed-forward layer. The first linear layer increases the dimensions of the feature space, and the second one brings it back to its initial dimensions. So here you have fully connected 1, here you have fully connected 2. This is your activation, right? So kind of like you would have a rel-u, but here it's a gel-u. You have the batch dimension, the patch dimension, and then the D, which is basically just what's coming out of the attention layer, right? And T of those, right? So it's the input is just D, but then you're basically doing this T equals 4 here. So you're gonna have, the output is going to be 4 times higher dimensional. You're going to feed it through your activation function, and then you're going to go back from this T times D into a D. So the input to this fully connected layer here is B by P by D, and the output of the fully connected layer 2 here is B by P by D, which is why you can take this residual connection here and concatenate them, right? Because the input shape here is the same as the output shape here. That's why you can just concatenate it like they're doing here, right? This little plus sign, that means that they're basically taking the value here and then adding it to the value here. It's called a residual connection or a skip connection sometimes. Okay. In this section, we investigate the preservation of patch-wise spatial information observed in visualizations of patch-wise feature activation levels. Bear some similarity to saliency maps. Visualized feature is strongly activated for almost all rocky patches, but not for patches that include the lizard. Even though every patch can influence the representation of every other patch, these representations remain local even for individual channels in deep layers of the network. Okay, so this is kind of what they're saying, where the relative position of different things in the image seems to persist longer in a vision transformer. So in a ConvNet, as you go higher and higher in the ConvNet, higher and higher in the kind of abstraction layers of a ConvNet, it very quickly loses a sense of like the relative positioning of things. But it seems like what they're saying here is that vision transformers, even if you go higher up here, right? So this is a relatively high layer. It still is very much kind of aware of the fact that this only activates on these parts of the image. So the like relative position of that in the original image is being persisted longer. VITs learn to preserve spatial information despite lacking the inductive bias of CNNs. Yeah, this is a better way of describing it here. So, for example, here you have in layer 1, right? So this is at the very beginning of the vision transformer. You have this kind of like sky activation map. Here's the actual image that's being fed in, and you see how the sky activation map, it's kind of mostly triggering on this part of the image here, which is kind of the light blue part here. And so on. You have layer 1, layer 4. So as we move from left to right here, we're going deeper and deeper into this transformer. And what they're really showing you here is that even in the very deepest parts of the transformer here, such as this layer 11 with the maracas, right? What they're saying is that this activation map here, right, which is showing you which parts of the image are triggering the most on this, it still has awareness, right? It's still saying, okay, this maraca pattern here, it's really activating the most here, right, where the two maracas cross, which is exactly what you would expect, right? So it's like the features are still kind of aware of the position of the things in the original image. I wish I had better words to describe this, and I'm sorry if these words are just not good, because there's a lot of like terms here that like they mean the same things, right? Like the word feature in deep learning, just like there's like a billion different definitions to that. Like anything could really be a feature, right? Any intermediate part of anything in a neural network you could describe as a feature. For each image triple, the visualization on top shows the result of our method. The image on the bottom left is the most activating image from the validation set, and the image in the bottom right shows the activation pattern. This one's actually cool. It looks like a crowd, right? You can see the little faces of people, and you can see how it's activating on this. So this is like the crowd activation map. And you can see in this image, which is like some kind of image of a guy like playing a guitar in front of a crowd, the activation is very precise, and it even crops out the guitar, so it knows that the guitar is not part of this crowd, which is quite cool. Last layer of the network departs from this behavior and appears to serve the role similar to average pooling. We include quantitative justification to support this claim. Figure 3b, last layer that is activated by shopping carts. The activation pattern is fairly uniform across the image. For classification purposes, VITs use a fully connected layer applied on only the class token. It's possible that the network globalizes information on the last layer to ensure that the class token has access to the entire image, but because the class token is treated the same as every other patch by the transformer, this seems to be achieved by globalizing across all tokens. So, average pooling, let's see if I can find a good picture of this, but yeah, this is a fine picture. I like this one. Here we go. So in a transformer, right, you're not in a transformer, in a convnet, you're applying these feature maps, right? So here you go. You have your image, and you're kind of applying these you're convolving these kernels across your image, and then you create these feature maps, and then you basically keep doing the same thing over and over again, and you end up with more and more channels and smaller and smaller width and height dimensions until you basically have this big stack of feature maps. And at some point, you're going to want to take this big stack of feature maps and turn it into a fully connected neural net here, right? Just like a very, very wide, one layer thick, or one neuron thick, or one neuron deep. I don't know, deep's not the right word here, but like a 1 by whatever, 768 neuron layer, right? This is usually called the head, right? This part here. So the problem is that this is going to get very high dimensional very quickly, right? So you don't want to have a ton of dimensions here when you actually go to this fully connected layer. So one way to reduce the total amount of kind of basically dimensions, but also like just numbers here, right? Just you want to get rid of some of the numbers here, is to do what's called pooling. And in pooling, you take, here for example, this is max pooling. You say, okay, I have I have a matrix here that's 4 by 4, and I can turn it into a 2 by 2 matrix by basically taking, for this purple section here, I'm just going to take the biggest one. For this yellow section here, I'm just going to take the biggest value. For this blue section here, I'm going to take the biggest value. And now you went from a 4 by 4 matrix into a 2 by 2 matrix. And max pooling, what it's really doing is you're basically saying, I don't really care about the activations that are small here, right? The only thing I care about is the activations that are big, right? I want to know if there's a big activation, if there's a big kind of neuron spike, right? Like if the neurons are telling me, like, right here, something important happened here. Look at this 8. This is a big number, like big spike here. So max pooling says, okay, I want just the biggest number from each of these little sections here, and also by doing that, I basically reduce the total amount of dimensions, which means that when I finally get to my fully connected layers here, the dimensionality is going to be something that I can actually handle. Average pooling is a similar kind of idea, but rather than taking the maximum one, you're basically going to just take the average here. So different results, right? In average pooling, from each, the average value selected or the maximum value selected, and depending on which one you pick, there's going to be different kind of behaviors there, right? So they're trying to draw an analogy here where basically the vision transformer is kind of doing this at the very last layer. So it is possible that the network globalizes information in the last layer to ensure that the class token has access to the entire image. What is going on with this highlighting? I think like the lines are just formatted weird. Okay. After the last layer, every patch contains the same information. Isolating class denotes the experiment where attention is only performed between patches before the final attention block, while patch average and patch maximum refer to the experiment in which the classification head is placed on top of individual patches without fine-tuning. Patch average, patch maximum. This is kind of cool. This is actually... So top 5 accuracy means as long as your guess is within the... As long as the actual answer to your classification is within the top 5 guesses of the of this model, right? So the model's going to give you a bunch of logits, right? A bunch of probabilities for each of the classes. It's going to say this image has a whatever, this probability to belong to this class, this probability to belong to that class, and so on. Top 1 means it has to get it right. Top 5 means as long as it's in the top 5, it's fine. So this is a much more kind of rewarding. That's why 97 is bigger than 84, 94 is bigger than 78. It's easier to get top 5. But the interesting thing here, classification head is placed on top of individual patches. So here they're not doing it at the very end. So they're not saying for every patch, right? Like we're going to basically combine all of them. Here they're going to put a classification head on top of each individual patch. And it's kind of interesting how this is like the same place. I thought this would be terrible, right? If you're only paying attention to a very small patch, how is it able to still get such a high classification score, such a high top 5 accuracy? And I think that's kind of what they were saying here, that actually vision transformers seem to be able to pay attention to the background better, where they can actually classify images based on the background a little bit better than ConvNets. Okay, so here they're messing with this class token and not passing it in until the very end, and so it's kind of like a weird architecture, and then they're showing you that even with this weird architecture they can still get a relatively high score. Class token captures mostly as the last layer. So I think this is true for a lot of things. Right, like I think in most ConvNets and most kind of deep learning models, the notion of individual classes, right, is really only, like if you have a dog and a cat classifier that classifies dogs and cats, the notion of dogs and cats really only exists at like these kind of higher layers. If you actually go into the lower layers, they're not thinking about dogs and cats. What they're thinking about is edges and textures and ears and eyes, and like basically just like more primitive, you can say high frequency type features. And then as you go higher up, this is where you're actually going to be looking at like kind of the class specific stuff. So I would almost say that this also applies to ConvNets, where global information is mostly happening at the later layers. Here they're specifically saying the last layer. Further confirming that the last layer performs a token mixing operation so that all tokens contain roughly identical information. Figure 7 contains a heat map depicting the performance of this setup. Where's figure 7? This is figure 8. This is figure 6. They skipped a figure. Or is it oh, here you go, figure 7, it's down here. Okay. Heat map of classification accuracy on the validation set when we applied the classification head trained to classify images on top of the class token to the other patches. I don't exactly know what I'm looking at here. I guess the information we can glean from this is that it's like, it's pretty spread out. It's not like there's like a very specific concentrated area. It's like the classification is like largely kind of consistent throughout the whole image, which means it's using the whole image. I guess that's how I interpret this. It's hard to say. I wish they'd showed us the actual image. Complexity of features versus depth in VIT-B32. Visualizations suggest that VITs are similar to CNNs and that they show, yeah, so this is actually what I was saying. They show a feature progression from textures to parts to objects as we progress from shallow to deep. Yeah, so early on in the layers you have things like textures, then you have objects here, or what they call parts, and then you have actual final things. So this is an actual coffee machine. Here you have like couches and chairs and ladders. Here you just have things like crowds, bottle tops, and then once you get to the actual lowest stuff, you have like kind of just rock texture, stringy object texture. We conclude by noting that the information structure of a VIT is remarkably similar to a CNN in the sense that the information is positionally encoded and preserved until the final layer. The final layer in VITs appears to behave as a learned global pooling operation that aggregates information from all patches, which is similar to the explicit average pooling counterparts in CNNs. As extensive work has been done to understand the workings of convolutional networks, including similar feature visualizations and image reconstruction techniques to those used here, we may be able to learn more about VIT behavior via indirect comparison or direct comparison to CNNs. An important observation is that in ConvNets, early layers recognize colors, edges, and textures, while deeper layers pick out increasingly complex structures. Yeah, I would say most people have a good intuition about that. VITs exhibit this kind of progressive specialization as well. I would say that all deep learning does that. That's the whole point of deep learning, is that there's a depth, right? The deep in deep learning refers to depth, where you have many layers of neurons, one on top of the other, right? ConvNets are a form of deep learning, and transformers are a form of deep learning, right? They're very different if you actually look like at the actual architectures. Transformers are very different from ConvNets, but they're also, if you zoom out, they're actually quite similar, right? At the end of the day, you have kind of layers of neurons on top of other layers, on top of other layers, on top of other layers. So it's like this fundamental concept of deep learning, of just having multiple layers, allows a learning objective to create these kind of like hierarchies of abstraction, right? Colors, then edges, then textures, and then deeper layers picking out increasingly complex structures. This is kind of the magic of deep learning. Okay, so they're looking at individual bounding boxes within ImageNet. in order to kind of compare the background and the foreground. So here, VIT B16 detects background features. Kind of what they're showing you here is that this vision transformer has activation or feature maps, or whatever you want to call these, has basically specific patterns for backgrounds, right? So you can see that this grass pattern is activating on this white stuff here, which is the background of this image of the wolf. So it's not just using the wolf itself to classify this as a wolf, it's also using the fact that it's on this kind of snowy grass, which is a specific pattern it's looking for. B, this is almost like an unrelated stuff. So B is unrelated to A, but here they're showing you, okay, to test out how much of the stuff is coming from the background and how much of the prediction is coming from the actual stuff, they basically did this kind of like masking, where they were like, okay, well, what happens if we just feed this, right? Like cropped out pictures of fish rather than having all this extra context of like the tarp and the grass and the water. So that's what they were trying to do with this experiment section here, is they're basically trying to compare how much of the prediction is coming from a foreground and how much is coming from the background. So here's the table that we want. So VITs more effectively correlate background information with the correct class. So here you have a bunch of different transformers, right? Different size transformers. And then here you have a bunch of conv nets. So these are mobile nets. This is a tiny little conv net. ResNet 152. This is a much bigger conv net. And you can see how these conv nets, if you actually compare them image to image, so full image, they're about the same. Like the transformers are a little bit better than the conv nets. But if you look at just the foreground and then just the background, here's where you notice the difference, right? Look at this. The transformer, just the foreground, it's pretty high, it's doing pretty good. If you just show it the wolf, it can figure out it's a wolf. But if you just show it the background, the snowy grass, it still does pretty good, right? Like 96 to 33. So it's paying attention to the background in a useful way. Versus a conv net, the conv net, if you just show it the wolf, 90%. So it's already dropping a lot, right? So like the conv net does actually seem to need the background more, but if you give it only the background, it actually performs terribly. So the conv net seems more fragile to patches, so masking. It needs really the full image, and it's specifically on the background, it's terrible. Kind of interesting to think about. This is like the best table in this whole paper. Inductive bias. Yes, I can say that. So inductive bias, inductive bias would be something like an example of inductive bias would be the translational invariance of CNNs. Let me see. Set of assumptions that the learner uses to predict outputs. So inductive bias convnet translation invariance. Here we go. Top 5 inductive biases. Group equivariant, spatial. Yeah, this is the one that I'm talking about. So in convolutional neural nets, right, you have this you have these little feature maps and you're convolving them across, right? So you decided to do that, right? As the scientist, you said, I'm going to take this little part of the image and I'm going to take this little matrix and then I'm going to multiply this little matrix as I slide it across my image, right? And you decided to do that because you think that within that image there's going to be the same thing but positioned in different places, right? So you decided, you made an assumption about images that translation doesn't matter, that a dog in this part of the image versus a dog in this part of the image is actually the same and it should still qualify as a dog. So you made an assumption, and then you're using that assumption to basically bias or kind of move your answer into a specific place, right? I feel like that's a terrible description, but let's see if this is a better description. Spatial bias is a type of inductive bias in convolutional neural networks that assumes a certain type of spatial structure is present in the data. According to its research, spatial bias can be useful even in a model that is non-connectionist and completely linear. Blah, blah, that's more terms. Okay, let's see something better here. This type of bias can be introduced with only minor changes to the algorithm and no externally imposed partitioning is required. So, yeah, I don't know. I'm trying to find a better description because a lot of times, like with these math definitions, like people just come up with a kind of a definition that just like describes it with even more math, and I feel like that's not a good definition. But like another kind of usual normal bias is like the Gaussian prior as inductive bias. Yeah, here you go. The inductive bias of a Gaussian process. So a lot of times in statistics, right, you have your Gaussian. And you just assume this, right? Like there's nothing magical. There's nothing that's saying that your data is going to look like this, right? Your data can very much not look like this, but a lot of statistics starts with an inductive bias that says, okay, well, actually, I'm going to design some process or some system or some kind of specific neural network architecture that assumes that my data looks like this, right? And that's a type of bias that you're putting in there, sometimes called a prior as well. I don't know, that was a terrible description, Nader, I'm sorry. I'm learning how to describe things and teach, but hopefully that helped you a little bit. All right, back to this paper. We observed that VITs are significantly better at CNNs and using the background information in an image. VITs also suffer noticeably less from the removal of the background. Rectangle containing, blah, blah, blah. Study the role of textures. See figure 16 for the decay and accuracy as textual information is removed. Where's figure 16? Figure 16 is in the appendices. Figure 12. Figure 17, so that means 16 is here. Figure 16. Low pass. So they apply a low pass filtering, which is basically just removing high frequency information, right? And as you increase the amount of low pass filtering, the performance of the resnets, the green and this orange here, start to get significantly worse, but the performance of the vision transformers gets higher. So this actually has interesting repercussions too, because it means that vision transformers are more robust to transfers or to shifts in the distribution. A lot of times in computer vision you'll have problems where the data that you train on is not necessarily the same as the data that you encounter in production. And one of the ways that happens is that the actual camera sensors are different, and because the camera sensors are different, the amount of like high frequency and low frequency like noise differs. So this VIT is being more robust to kind of removal of high frequency information means that they're probably better able to generalize outside of their data distribution when it comes to camera like fuzziness and like camera specific stuff, which is good to know. Okay, this is actually this section here. Now they're going to actually be looking at how the features inside a vision transformer are affected by doing this contrastive language image pre-training. With and without clip, to study the effect of natural language supervision on the transformer-based backbone. Training objective for clip models consists of matching the correct caption from a list of options with an input image. Feature optimization shows images from an elevated vantage point. Okay, so because these in this case, the vision transformers also have a the final embedding space that is the results of a clip training. Because you can also basically go from text to a specific point in that embedding space, they can now say, okay, well, rather than saying what image maximally activates this particular point in my transformer, you can say, well, what parts of my transformer are kind of maximally activated with the vector that results from me feeding the word from above into a clip, right? So there's like the image part of clip, and then there's the language part of clip, and both of them project into the same embedding space. So here they're saying, I'm going to take the word from above, I'm going to project into that embedding space, I'm going to get that embedding vector, and I'm going to now go backwards from there through my vision transformer and see what is actually activating it. So here they're saying the word from above, and you can actually see here that the resulting feature map inside the image part of the clip system has kind of this notion of like from the top. And then when they left feature sharp boundaries, right, where is it though? Maximally activating ImageNet examples. Okay, so these here, this is the actual, so this is from above in vision transformer, right? This is the little activation feature map or feature activation map or whatever they want to call it. And then the two images on the right for each set here are basically the ImageNet examples that maximally activate this. So what they're really kind of excited here is that it's not like a ConvNet, right, where basically like you would expect the two images that maximally activate a specific activation pattern to be very similar visually, right? Here, these two images, the way that they're similar in that the notion of kind of from above is there. So this activation map here is actually like has some notion of a semantic concept rather than a notion of a specific visual pattern, which is kind of crazy. These figures are just like not good though. Like you can't have A, B, and C and then 3 parts to A, B, and C and then describe left, middle, right. Like what is going on here? Like you know, this is like a weird 3x3 grid being described in a I don't know. I disagree with like kind of the way that this. I understand what they're trying to show you with this figure, but I think it's like kind of unnecessarily confusing in this format. Shows the image optimized to maximally activate a feature in the 5th layer of a VIT clip model alongside its 2 highest activating examples. Presence of features that represent conceptual categories is another consequence of clip training. Clip-trained VITs produce features in the deeper layers activated by objects in clearly discernible conceptual categories. I would actually suggest that this might be the case in ConvNets as well. I think if you use contrastive language, image pre-training, or other similar kinds of contrastive learning on a ConvNet, you would also see features in the deeper layers that correspond to concepts. I don't think this is unique to vision transformers. I think this is just the process of the clip training. We introduce a vision framework for optimization-based feature visualization. We then identify which components of a VIT are most amenable to producing interpretable images, finding that the high dimensional interprojection of the feed-forward layer is suitable, while the key, query, and value features of self-attention are not. So if you want to make your own saliency maps for your own transformers that you design in your work, here is kind of actually the key part that you can get from this paper, is that the specific layer that you want to be using for your transformer saliency maps is the little feed forward layers that are in between, kind of at the end of the little transformer block. You don't want to be using the key, query, and value tensors inside that transformer block. VITs preserve spatial information of the patches across all layers, with the exception of the last layer. I would say this is not necessarily the case. I think a lot of vision transformers use positional encodings. VITs make better use of background information and are able to make vastly superior predictions. Okay. Cool paper. It's a little rough on the edges. I think that they went a little bit deep on the terminology. A lot of the figures were a little bit confusing, just the way that they were designed. I'd love to see this, right? Like this blog post here. Very highly recommend it. There's a couple different blog posts like this. Distill is like a blog post for Google research. Yeah, it's a little bit old now. They haven't really put anything in there. But, you know, this is what you really want, you know, like this, with these type of like nice, clean figures showing you stuff like this. Like here you have the activation map for dogs or snouts, balls. Like, I'd love to see this kind of blog post, but for transformers. That would be interesting to me. Like this is just not as clean. It's like kind of hard to see what is going on here. Yeah, so here they're showing you that it's harder to use the keys queries. Are you actively working as an ML engineer? Yes, I am. If you have any ML work to do, I am available for consulting and contracting. Let me know, man. If you want machine learning stuff done, I'm happy to get on a call, and you know, the first call's always free. I can help you analyze your problem and help you kind of guide you to a direction, and if I'm the right guy to implement that particular thing, I will 100% help you with that. And just let me know. However, in deeper layers, the features are entangled. Okay, these are the different models that they tried. Look at these are crazy. You have like snowy grass. Here you have keyboard. You have fence. Here you have higher layers, so these are higher up in the transformer, so now you're no longer just looking at textures and patterns, but now it's actually like whole objects. So here you have the maracas, here you have the worm camera. Yeah, these are probably the most interesting here. This is the highest layers. So higher up in the transformer stack, with the clip training. So these are like the concepts. So you have your legs, iguana face, human face, bottle tops. One-on-one coaching? Depends. I work for highest bidder and most interesting stuff. Yeah, if I can do one-to-one coaching if you're interested, but you know, at the end of the day, if someone wants to pay me like $10,000 to solve like an industrial inspection task, and you just want to pay me like $2 to help you coach or to coach you, I'm probably going to take the $10,000 industrial inspection task. So, you know, I try to, I'll give you, if you want to meet, I'll like help you, right? And even for something like coaching, I can just show you different websites that you can go on and you can learn, different YouTube channels that are good for learning. Learning is actually easy, man. You don't need to pay people to teach you. I don't think you need, like, don't feel like you need to pay someone to do one-to-one coaching. I think the internet is more than big enough for you to learn everything you want about deep learning. Yeah, I would say most of what I do is basically just for industrial boring applications and startups and like stuff like that. Cool. Well, that was what do vision transformers learn. A little rough around the edges. It's a preprint, but they'll probably come out with cooler stuff. Yeah, interesting little paper. Thanks for listening, guys. If you want, you can definitely reach out to me. So who.po.xyz@gmail.com. Feel free to email that and I will answer you. Again, yeah, happy to meet and discuss, and maybe I can help you, maybe not, but we can figure that out. Thanks for watching. Like and subscribe, and have a great weekend.